Hello, my name is Maria, and today I'll be talking about polyhydroalkanate, or PHAs, a class of biodegradable plastics that are gaining popularity as sustainable alternatives to conventional materials. So, what are PHAs? PHAs, or polyhydroalkanoates, are a group of biodegradable thermoplastics made from renewable sources like plant sugars and oils. They're designed to break down naturally in environments such as soil, water, or compost, leaving behind no toxic residues or microplastics. Unlike petroleum-based plastics, PHAs don't persist in the environment for centuries. They maintain the durability and flexibility like traditional plastics, but with the added advantage of full biodegradability. PHAs are already being used in a range of products, like compostable packaging and agricultural films, making them a leading candidate for sustainable material design. For the structure, I will be focusing on PHP since it's one of the most known PHAs. PHP is a linear polyester made up of repeating units of 3-hydroxybutyrate monomers. Each monomer contains a hydroxyl group and a carboxylic acid group, which react to form an ester bond during the polymerization. This ester linkage is critical, as it forms the backbone of the PHP polymer and is also what makes the material biodegradable. In the presence of moisture or microbial enzymes, these ester bonds can be broken down, leading to decomposition. Now let's take a closer look at the material properties of PHP. PHP is a semicrystalline thermoplastic with a relatively high degree of crystallinity, typically around 70 to 80% as I mentioned on the previous slide. This contributes to brittleness and a rigid mechanical behavior, making it similar in strength to some conventional plastics like polypropylene. In terms of mechanical strength, PHP has a tensile strength of about 30 to 40 megapascals, which puts it at the same range as polypropylene. However, it has a low elongation at break, meaning it doesn't stretch much before it breaks. This makes it a little bit brittle, as I mentioned before. Its melting temperature is fairly high for a bioplastic, around 175 to 180 degrees Celsius, which means that it can be processed using conventional plastic equipment. However, it also has a narrow processing window. If the temperature is just a bit too high, it degrades thermally, which can release unpleasant odors and reduce performance. Another important feature is its glass transition temperature, which is around 5 degrees Celsius, and this means that the PHP becomes brittle at cooler temperatures. From a barrier property standpoint, PHP has good resistance to oxygen permeation, which makes it useful for food packaging applications. And lastly, its biodegradability is a major strength. PHP breaks down in soil, compost, and even marine environments, thanks to the microbial enzymes that can cleave the ester linkages in the backbone. PHAs aren't just biodegradable, they're versatile. Thanks to their material properties, they're finding real-world applications across several industries. For example, PHAs are biocompatible, which means that they can safely interact with the human body. This makes them ideal for medical uses, including absorbable sutures, drug carriers, and even tissue scaffolds that slowly degrade as healing occurs, as the one we see in the picture on the slide. Their strong barrier against oxygen makes them useful in food packaging as well, where they can help preserve freshness in biodegradable containers. At the same time, they're not great water barriers, which actually helps in composting. In agriculture, PHAs are used in mulch films that naturally degrade in soil after harvest, removing the need for labor-intensive plastic collection. Finally, because PHAs can be thermoformed at around 180 degrees Celsius, they're increasingly used for single-use customer products, like compostable straws, cups, and utensils. So while the material itself is special, it's the combination of biodegradability and performance that makes PHA practical in these areas. For the experimental part of my project, I wanted to see how a PHA straw would behave in a real-world composting environment. So I buried a commercially available PHA straw in my home compost pile. I took out a container of compost where I put pieces of straws into the compost and waited for 2 weeks to see if it would compose. This compost includes typical household organic waste like food scraps, coffee grounds, leaves, and yard trimmings. It's kept in a warm, shaded area and stays naturally moist, which creates an ideal condition for microbial activity. After 2 weeks, I removed the straw pieces to check their condition. One of the most noticeable changes is that the straw has become more brittle. When I gently applied pressure, it no longer had the same flexibility and it felt stiffer. It also cracked more easily, and I noticed that some of the straws had cracked on the sides, and the surface also appeared slightly duller and rougher. This indicates early surface level degradation, which means it's a good sign and suggests that the straw is beginning to break down at the molecular level. While full decomposition will take more time, this early result supports the claim that PHAs are home compostable and environmentally safe alternatives to traditional plastics. To conclude, PHP is more than just a biodegradable plastic. It is a functional material with real potential in multiple industries. Its structure is what makes it unique. The ester bonds and short side chains give it strength and crystallinity, but also allow it to break down naturally under the right conditions. In my experiment, I observed that after 2 weeks in compost, the straw became noticeably more brittle, and this physical change supports the idea that degradation is already happening. This project reminded me that material science is not just about how things are made. It's also about how they behave, how they break down, and how we can design better materials for a more sustainable future. Thank you.